Hello, this is a tutorial video on how to use the Analog Discovery USB oscilloscope from Digilent Incorporated to act as an oscilloscope for your ECE 3434 Electronic Circuits Laboratory. It is anticipated that you would use some of the functions of this scope instead of the bench scope that is already found in the lab. To demonstrate this USB oscilloscope, I'm going to use experiment number 1 from ECE 3424. This uses a simple op-amp that is configured in a non-inverting amplifier configuration, and initially is going to be configured with a gain of about 19. What we're going to do is we're going to use the Digilent Analog Discovery as the oscilloscope for this project, and we're also going to use it to provide the input waveform for this project. So we're going to replace the bench scope, which is this wire right here and this wire right here, and the function generator with the Analog Discovery. We are not going to use the Analog Discovery to power the op-amp because this experiment requires plus or minus 12 volt supplies, and the Analog Discovery only has plus or minus 5 volt supply. Now let's connect our Analog Discovery to our circuit. During this discussion, I'm going to be referring to this Analog Discovery pinout, which is available on the Digilent Inc. website. Now let's connect our oscilloscope and waveform generator to the circuit. We have two scope channels connected here. Here's channel 1, and this is the ground for channel 1, and here's channel 2, and this is the ground for channel 2. So for the channel 1 input, that is connected to the input of our circuit, this RX resistor. So we're going to take this scope channel 1 positive, and we're going to connect it here to the input of our circuit. For scope channel 1 negative, which is that's going to be the ground for our scope, we're going to connect that to our ground rail right along here. For channel 2, which is blue, we're going to take the blue channel 2 positive, which is going to be here, and this is going to be connected to the output of our circuit. Scope channel 2 negative, which is this blue white wire right here, is going to be connected to our ground rail here. Now we need to provide an input waveform to our circuit. The input waveform is going to come in via this lead. We're going to use the waveform generator 1 on the Analog Discovery to provide that input waveform. So you'll connect this yellow wire here to the signal input here, and you'll connect this black wire here, which is the ground for the waveform generator, to the ground rail of your circuit. So here it's shown here. I also want to point out that in this circuit they show this resistor here between our input waveform and the input of our circuit. In my circuit, what I've done is I have removed that. That's this resistor right here. I simply removed that and just have a bare wire going from here to here so that our waveform generator is directly driving the input. So now let's start the Analog Discovery waveform software. So it's called Waveforms. I'm going to go ahead and start it up here. When you start it up, if you have your device plugged in, it will detect it, and you will get this little panel right here that shows you your analog instruments and your digital instruments. In this demonstration, I'm only going to show you the scope instrument and the waveform generator instrument. So let's go ahead and get those started. I'll double click. I'll open it up. Pop up. I'll adjust it. I'll also open up the waveform generator. And so here are two instruments that we're going to run. These should be off when you start them up, and these buttons right here will turn them on. Before we turn on our instruments, let's configure them. For the waveform generator, we're going to want a 1 kilohertz sine wave. So I have a sine wave selected here. For the amplitude, let's go ahead and choose a 200 millivolt amplitude. That will give us a 400 millivolt peak-to-peak signal. 200 millivolts positive, minus 200 negative. In the offset, let's make sure that we have a 0 DC offset. In the oscilloscope, let's go ahead and enable channel 1 and channel 2 by having these clicked. We want the offset for both of these to be 0 volts. We want the volts per division to be 1 volt per division initially. For our time base, we're going to want to have a 1 millisecond per division time base that will specify our horizontal tick marks. For our mode, let's make that auto source. We're going to make this channel 1. This is our trigger source. We'll talk about what a scope trigger is in just a minute. Our condition is going to be rising waveform. And for level, let's go ahead and put our trigger level at 0 right now. Alright, I'm assuming that your circuit's powered on, so let's go ahead and enable both our instruments. So we'll turn on the waveform generator, and we'll turn this on, and voila, we have a waveform. So it looks, the channel 1 happens to be our input waveform. It's 400 millivolts peak to peak. It looks very small here because we have 1 volt per division. Our output waveform is blue. That's channel 2. And it should be about 19 times larger than this from peak to peak. That's the way I have the circuit configured. So it looks like our circuit is operating. This is a non-inverting amplifier, and sure enough, these waveforms are not inverted from each other. Now let's talk about some of these scope controls. First thing we want to do is we want to change this horizontal scale on channel 1 to be able to see a little bit more of this waveform. So I'm going to change channel 1 from 1 volt per division to 200 millivolts per division, and that will expand this waveform a bit so we can see it better. This horizontal scale right here, when I have channel 1 click, is going to be for channel 1. If I click on channel 2 here, then I'll see the volts per division for channel 2. If I want to change the time base, I can change this. If I want to see fewer cycles, I'll go to a faster time base. So I'll go down to, say, 100 microseconds per division. 100 microseconds per division here is going to give me 500 microseconds here, 500 microseconds there. It's a total of 1 millisecond. 1 millisecond is the period of a 1 kilohertz waveform, so I'm only seeing 1 cycle of this waveform. I'll go ahead and go back to seeing multiple cycles of the waveform, or going back to 1 millisecond per division. Now let's talk about scope triggering. Scope triggering means the conditions that are necessary for the scope to capture a waveform. This scope is actively capturing a waveform because we have a green trigger signal here, and we see that our sample number is continually changing as it's continually grabbing new data on its inputs. So what controls scope triggering? There are 4 conditions here that actually that control scope triggering. First is the mode between auto and normal. We'll talk about this in a second. The second is where are we getting the trigger source from? You typically only use channel 1 or channel 2. We're going to use channel 1. We're going to be triggering on this waveform right here. Then we can choose an edge, rising or falling. For a sinusoidal waveform, it doesn't really matter, so we just arbitrarily choose rising. And probably one of the most important ones is the trigger level. This says whenever I see a rising waveform cross 0 volts, then trigger and capture data. So how does this trigger level set? This control right here is going to set the trigger level. I just raise it. Now it's 60 millivolts. Let's go ahead and raise the trigger level out of the bounds of this waveform and see what happens. What will happen is this went to armed, and now the waveform is simply kind of jittery. Let's put it back within the bounds of the waveform. We see it's triggered, and now it's synchronized. Why does the waveform become jittery when I move it out? Well, what's happening is when I move it out, it no longer sees the condition for a trigger. However, this mode right here says automatic, and so since it no longer sees the condition for a trigger, which says I don't see a rising waveform crossing 900 millivolts, then it just, because I'm in automatic mode, it simply automatically captures data out there. And because my sampling right here is different than the frequency of my waveform, it's going to be jittery. I can't synchronize my capture to displaying a steady signal on here. So I have to satisfy the trigger conditions if I actually want to get a steady signal. Now, what is the difference between auto and normal? Well, if I put it in normal, let's see what happens that's different from before. I'm going to take the trigger level and move it out of range. This becomes armed, and then it just stays there. It says that if I don't see anything trigger, this is trigger, I'm not going to capture any data from the external input. So essentially, it freezes the last thing that it captured. So I can go back here, and it's going to start actively capturing again. It's triggering. If I turn off the waveform generator, then it's going to say armed. It's not triggering anymore, and it's frozen the last thing that I captured. So let's go ahead and run it again. So now we're running, and now we're actively triggering again. Let's put this thing back to auto. And what's going to happen when I stop the waveform generator? Well, it's going to lose trigger. It's going to go to arm status, and then it's going to say, hey, I don't see a trigger anymore, so I'm going to do auto, and now there's nothing because I've stopped my waveform generator. So I'm going to go ahead and run the waveform generator again, and now here's my waveforms back again. So I would suggest in your labs that you use auto as your mode most of the time, because auto will always show you what's out there, and then based upon what you see, you can adjust your time base and you can adjust your volts per division. Now let's talk about making measurements, as you'll have to make lots of measurements in electronics lab. So I'm going to click on this and open up the measurements pane. And when I do that, I get the ability to add a measurement here for either channel 1 or channel 2. Let's click on channel 1. A vertical measurement will measure voltage. I'm going to select peak to peak and say add. Let's go ahead and add a frequency measurement as well. So that's going to be a horizontal measurement. So I'm going to click on this, horizontal, click on frequency. I'm going to add that. So that'll be the frequency of channel 1. I'll go ahead while I'm here. I'll add a peak-to-peak measurement for channel 2. So I'll go back and open vertical, open peak-to-peak, and add that. And then I'll close this, and now I have some measurements. So you can see that I'm now measuring peak-to-peak and both channel 1 and channel 2. When you're copying down values from here, you might get a little jitter here. If you want to stabilize this, you can copy down some value. You can eyeball it and get an average, or you can change this to normal mode and then just move it out of the trigger condition, and it will freeze it, and then you can get a value that you can grab, and you can look at this a couple of times and see what you want to get. In this case, I would probably put down 3 significant digits of about I would round that to 5. I'd probably put down 7.75 for the peak to peak of channel 2. For channel 1, I'm sorry, for channel 1, I would put down probably about 402 millivolts. I said the gain of this is about 19. Let's see if that's true. So I'm going to go ahead and take 7.75 divided by 0.402. See what my gain is. I get a gain of 19.3. So that's close enough. Occasionally, you'll be asked to use your scope in what's known as XY mode. What XY mode means is that instead of using time as the x-axis, that you use one of your scope channels as your x-axis. This is very easy to do with this instrument. All you do is click on the Add XY button here, and it will show you a little small XY window, and it will allow you to put one channel or the other as the x-axis. Here I have channel 1 as the x-axis and channel 2 as the y-axis. If I wanted to flip that, I could just click here and it flips it. So let's go back to the original, so we have that. And now let's expand this out by dragging it over here. And let's talk about what this means. Well, because my channel 1 waveform is varying between 200 millivolts to minus 200 millivolts, this is going to be the limit of my x-axis, while my y-axis is going to be the full swing of the channel 2, which is going from approximately 4 volts, minus 4 volts to 4 volts. So while this doesn't look very useful to you right now, it will be useful in other labs. So just remember that when you have to put your scope in XY mode, it's this button right here that does it, and it makes it very easy to do that on this scope. I can go back to the main time view here or switch back to the XY view, either way, and it's readily available. Another useful function is the zoom window. I'm going to click on zoom and pop up the zoom window. And you'll see a zoom area appear on the main waveform window. I'm going to go ahead and move this around. Things that this is useful for is measuring the delta between the two horizontal bars or the delta between the two vertical bars. The delta between the two horizontal bars will give you voltage. The delta between the two vertical bars will give you time. Let's say that I wanted to measure the time difference between these two zero crossings on this waveform. I'd move the zoom around until this vertical bar was even with this crossing point. Then I would resize this so that, let me go ahead and resize it so that so the other crossing point is on this vertical bar here. And now I want to measure the distance between these 2 points. I can go to the zoom window over here, and I can add a measurement. So let's do that. And the time is going to be global. So I'm gonna measure the time between the two cursors, which are the left and right cursors. So I'm going to measure the delta between those, and I'll add it. So that tells me that the time between this zero crossing and this zero crossing is about 508 microseconds. That's reasonable because this is a 1 kilohertz waveform, and the period is 1 millisecond. So 1/2 of that time would be approximately 500 microseconds. Another interesting capability of this instrument is the audio capability. I'm going to open the audio panel here. This is on channel 2, and this allows you to listen to your waveform. So I'm going to go ahead and click play here, and now I can listen to what this waveform. But in order to do that, I need to actually see a lot more cycles of this waveform. So I'm going to, in order to actually hear anything, so I'm going to go ahead and turn this down to a much lower time base, so I can actually see many more cycles. And now what I'm hearing is a tone in my headset for the 1 kilohertz tone. I can go down to a lower tone, 200 hertz, now much deeper, and I can essentially give myself a hearing test if I want to by going up to higher frequencies until I can't hear it any longer. So that's an interesting capability. If you were sampling voice, then you could actually hear voice audio via this way. So another interesting capability is to play audio files through the waveform generator. So here what I've done now, from standard, I've selected player, and I went ahead and used this browse function to browse to a file called eaglesfastlane.wave. So this is the song Life in the Fast Lane from the rock band Eagles. So I can select that, and then I can go ahead and run it. And you can't see a preview here, but if I come here, then I can see it on the scope. And if I wanted to listen to it, I could go to my audio mode here, and I could say play, or I could be listening to it by clicking on the play button. I'm not hearing anything right now. In order to hear something, I'm going to have to go down to much slower. And when I do that, I can, in my headphone, I can start hearing the music. It's a little choppy because it is sampling, but it's definitely understandable as the rock song Life in the Fast Lane. So that's sort of cool. Besides the oscilloscope instrument, there are some other interesting instruments here. I'm just going to look at the spectrum analyzer real quick. The spectrum analyzer can show you the spectrum of a signal. It's going to use the scope input channels here for making measurements. And so when I run this, it's going to take over my scope input channels. I can display here this frequency content of the input signal, and I can choose different ranges here. The lowest range is 10 kilohertz to 24 kilohertz, and it's going to put the center frequency here, which is going to be right here at 5 kilohertz. So let's go ahead and set our input frequency of 1 kilohertz and run this. So I'm going to start running. So it's showing me a spike of energy at this point here. If this point is 5 kilohertz, I have 5, 4, 3, 2, 1 kilohertz. Sure enough, that's 1 kilohertz. There's very little frequency content, or no frequency content in the signal besides that. So I'm looking at 1 kilohertz value here. Let's go ahead and move this around. Let's go ahead and put this at 2 kilohertz. And we can see now that we have it at 2 kilohertz. If we put it at 5, it should show it right in our center. And sure enough, it does. So let's do one last thing. Here, let's see, we have our 1 kilohertz sine wave being displayed here. Let's go ahead and see what the sweep mode does. What sweep does is you can sweep the frequency from some starting point to some stopping point in this amount of time. If I turn damping on, this also sweeps the amplitude in some amount of time. So I'm going to go ahead and put damping off, and I'm going to take a look at my signal. And it may not be obvious to you, but the frequency here is changing. Let's take a look at this with the spectrum analyzer. So let's bring that up. So if I bring the spectrum analyzer up and turn it on, our center frequency is 5 kilohertz. So here's 5 kilohertz. So we have 5, 4, 3, 2, 1. Here's 5, 6, 7, 8, 9, 10. So we definitely see that we have frequency content at all of those frequencies. So that includes this brief introduction of some of the capabilities of this instrument. We have not even touched on the capabilities of the digital instruments available with the Analog Discovery, such as the logic analyzer and our pattern generator. These capabilities would be very useful in courses like microprocessors, embedded systems, and senior design. Have fun with your instrument, and don't be afraid to explore its capabilities.